It's my great pleasure to welcome Dr. Svitlana Volkova to our CI Compass webinar series. She serves as the Chief of AI in Aptima's Office of Science and Technology. She spearheads the company's initiatives to develop trustworthy and human-centric AI systems that tackle complex real-world problems for the Department of Defense and other government agencies. Her research focuses on advancing natural language processing and machine learning techniques, with an emphasis on graph neural networks, causal inference, and multimodal models. Her work has pioneered methods for AI-powered analytics to explain complex social systems and behaviors. She's a recognized expert in human-centered AI design, evaluation, and developing trustworthy AI systems. And she has led many projects and has received a number of awards. And so, Svitlana, I'd like to welcome you warmly to this webinar, and we look forward to listening to your presentation about compound AI for cross-disciplinary discovery and research facility automation. Welcome.
Thank you, Eva. It's my pleasure to be here, and feel free to interrupt me, ask any questions. I will try to watch the hands in chat. Today, I wanted to tell you more about our recent work that is focusing on developing compound AI systems and evaluating the specific application for scientific discovery, and also kind of outline the limitations, the current limitations, and the potential of compound AI systems for research facility and research workflow automation. So let me start with kind of like an executive summary slide. Let's try to define what a compound AI system means. We all know that we live in the era right now of generative AI, and I will cover the historical advancements over the historical means the last 2 years. A lot of changes happened. The compound AI term was coined by the Berkeley lab, and it's a system that contains frontier models, which is large language models or vision language models or video models. It has retrieval augmented generation backend, and it also has agents and tools to make sure that all of this is working together. So that's how the compound AI systems are defined. And the second point I wanted to make is about automated research workflows. What do we mean by that? So we are creating technologies to enable scientists to focus on innovation, while agents are doing the work in the back end and focusing more on integration and the hypothesis generation, the experimental validation. So kind of connecting pipes in the back end, working with the data workflows, with the tools, with resource allocation and things like that. A third point is about cross-disciplinary synthesis. All research is fundamentally cross-disciplinary, and that's where the innovation emerges. That's why it's super important to develop systems that allow us to break the silos and make sure that we are creating connections, whether it was the agents or other techniques, models across disciplines. And finally, humans are not going to disappear anywhere near time soon, especially for scientific discovery. So human AI teaming is really important. We need to create trusted partnerships where compound AI system augment the scientists and the end users, and making sure that these relationships are safe and reliable. On the right-hand side, I'm showing you the visual of kind of the envisioned future here. So in a few years, we expect the reduction of time for scientific discovery, and in the increase of cross-disciplinary artifacts, whether these are databases, code repositories, or publications. There is a lot of there is huge economic value in developing these agent-based AI systems. And what's also important that the compound and agentic AI can give us is the improvement in experimental reproducibility, and in general, the integration. We already see from industry, we're seeing a huge improvement in terms of document workflow using agentic AI, which can be inherited and adopted by the scientific workflows and scientific infrastructure. Let's go a couple years back and and review like what get us here, where we are. So I'm showing you very famous visualization of LLMs with like different architectures. It's probably outdated. It's half a year old probably. But what got us where we are? So first of all, large amounts of data and large amount of compute, the efficient transformer architecture, and the way that we interact with these models, right? So in context learning it blurs the line between the model developer and the model user, and everyone can use these frontier models right now. Then over the last year, the mixture of expert training significantly changed the way that the systems are trained. The AI agents became a thing, and then the agentic AI workflows, it's where we are right now. So if you look in 2024 was the year of frontier models. It started with GPT-4o, and then we have Llama, which is Llama 3, which is an open source model. There was a release of the Claude model, which is a multimodal model. And towards the end of 2024, the reasoning models, like one from OpenAI, appeared. And that was all about 2024, right? So we were on the way to the multimodal. Multimodal means like images and text for now, but we were getting there. So 2025 is fundamentally the year of AI agents and agentic AI workflows. OpenAI released the deep research agent that allows the agents to go and do research. Claude also already has a feature which is called research, that can go and grab papers for you, and it can call into different APIs and can do research autonomously for you. Also, in 2025, we saw the DeepSeek release, which made quite a big splash. And we also seeing a lot of emergence of this multi-agent platforms like AutoGen from Microsoft. And a couple days ago, literally, we heard another update on the Stargate, about the Stargate project and about the research resource allocation and significant investment that is made by the government in order to make sure that we have resources to train these models for national security applications. Let me quickly go over what we mean by AI agents versus agentic workflows. So as you can hear, agents, you can think about them as LLM wrappers to start, but they are way more than just like LLMs. You can't call an LLM an agent. The agents, they perceive, they reason, and they act autonomously. They do have memory, and the different people are representing these memories differently. But agentic AI workflows is putting these agents together and making sure that they are acting jointly, right? So there is some orchestration behind the scene. And this a few cool papers that I'm citing here that make this core distinction between, because right now when we hear people say AI agents and the purpose of the agents and the way that these agents are developed versus agentic workflows, this is slightly different things and slightly different level of maturity and the purpose. If you look into the way that industry is using AI agents and agentic AI workflows right now, even if you look into the last month's April, every like company, Meta or Amazon or IBM, they not only have their own platforms for agent orchestration and agentic AI workflow orchestration, but they also developing different ways to make these agents better and smarter and better reasoning and reasoners and so on. So on the right-hand side, I'm showing you primary use cases from industry. Voice agents is a big thing in industry right now. Workflow automation, and by workflow automation, we mean primarily document workflows and things that are happening in enterprise. RAG, agentic RAG is a big thing, which means that every company, every customer can bring the data to the model, right? And basically hook up the agentic workflows to the retrieval augmented generated backend where the company's data is stored and so on. Computer use agents and coding agents is also a big thing. And I think last week, Claude released the next version, Claude 4, which is, I believe, the best coding agent that exists today. And finally, tool-based agents. And tool-based agents are important for enterprise, but they also important for scientific research workflows, which means that if I have my chemistry tool or my molecular biology or material science tool that I have been using for years, I can develop agents that allow me to interact with these tools and bring these tools into the process of scientific discovery and allow better automation. So let's kind of go deeper. What can we learn from the advancements that have been happening in industry literally in 2025 in terms of agentic AI? And what does it mean for research workflow automation? So modern research infrastructure requires automation to be scalable. The amount of data, the massive data sets, and they are fundamentally multimodal. They have to be handled properly, and experiments have to be run concurrently, which is a big challenge. Interoperability is the next requirement. So we need to create the way that can connect the diverse instruments and databases and tools, reproducible, which is harder to achieve with LLMs and other types of agents. But for scientific discovery, it's a must. Every workflow step has to be tracked and repeated. Intelligence, automation is possible, and we see a lot of progress from industry, so automatically optimizing resource allocation and finding anomalies. And finally, like transparency, providing real-time monitoring. We need to track the experiment progress and being able to intervene if needed. So these are the requirements and needs that are quite different and more challenging, I believe, compared to what industry is facing and trying to solve right now. So if we think about what type of agents we might need for scientific workflow automation and scientific discovery and innovation, obviously AI-driven comes to mind. And you can think about how we can provide the unified access to these agents to enable cross-disciplinary collaborative research. How do we create optimizing workflows to adapt to challenging needs, specifically focusing on research workflow automation? What are the questions and how do we build in data governance and security? And that's a big aspect right now that is unsolved at all. Agent safety and security challenging. We also have some sensitive research areas. So how are we compliant with the sensitive data, with the sensitive models, and going beyond like GovCloud deployments? Another challenging question, how do we assess the impact of automation, right? How do we actually measure that this AI system bring increased productivity and save time? And finally, how do we create these modular frameworks that scale across disciplines and institutions and connect different things? So that's what I hope I can get us closer during this talk and tell you more about the compound AI system and the system that we started building that I think is getting us closer to this vision. As I mentioned, the compound AI system term, which is not the same as a frontier model or foundation model, it was coined by the Berkeley team, I think in 2024. And if you look into major advancement in the science domain, like AlphaCode or AlphaGeometry, you see that it's almost never like a single model that is getting the performance needed. It's very often a very complicated back-end orchestration of models, agents, tools, retrieval augmented generation. 60% of LLM applications back in 2024 were using retrieval augmented generation. And these are complex, like multi-chain, like pipelines that enable this reasoning and multimodal discovery for all of these compound AI systems. And people started thinking about it also a couple years ago. So there was a really cool paper, it's called ChemCrow, about augmenting LLMs with chemistry tools. So these are the two papers for chemistry, where you can see it's a early version of a compound AI system. Back then, there was no such term. But as you can see that there are different these are pipelines or workflows where you have planning, automation, code execution, and this is specifically for chemistry. Similarly, for biology and biomedical research, recent paper from Stanford from a couple months ago puts together multidisciplinary teams. Again, it's a vision paper. It hasn't been implemented yet or tested, but you see that people like PI and then different domain experts, immunologists, machine learning expert, and so on, they're working together. And a really cool paper, I believe it's also from, this one is from Harvard on the right-hand side, that is trying to describe these different workflows like brainstorming or expert consultation or self-driving lab that put different agents, tools, models, in humans all together. And also in AI ML research, recent papers. There was the first paper. It was called AI Scientist, but I just grabbed the second version of the AI Scientist paper from last month, and also a similar work from Hopkins Agent Laboratory that uses LLM agents as research assistants. So it's kind of following up on the initial Stanford paper about simulacra and using LLMs as agents, which was back then, 2 years ago, just a wrapper for the LLM, not their full agent with behaviors, decisions, memory, and so on. But a lot has been happening, and a lot has been happening in this space for across disciplines, as I showed you, for chemistry, for biomedical research, and AI ML, where models, agents, tools, humans can work together to write a paper, to do to make a discovery, and I'm going to show you some recent work from Future House and so on. And let me show you what we've done in this space. So this is a demonstration of a DARPA-funded effort that is focusing on cross-disciplinary knowledge discovery and synthesis. And I'm going to go deeper and tell you how we implemented it. So it's a compound AI framework that includes frontier models. It includes agents and tools. You can search the web, you can query Wikipedia. Fundamentally, what's different with our system is that we're using user-centric design, and we start with the workflows the user needs. And then you issue a query, and we have an orchestrator that allows us to go and call specific types of agents given the query, and then return the answer back to the scientist and go back and forth with the scientist or a group of scientists to make sure that we either summarizing the knowledge depending on the query, or we brainstorming, or we filling research gaps, and so on. So it's a multimodal system. It's a prototype, but it's a multimodal system that enables this chat back and forth, and enables the call and access to specific scientific papers or other scientific artifacts like databases or tools. So it's called BioSage, and it was funded by DARPA. And let me tell you what progress industry had made in this space, and kind of go deeper into what's behind the hood of the system. So industry has also been working on bringing more research workflows and reasoning into their agents and agentic AI. Startup called Future House, they released multiple types of agents. They have like a search agent or deep search, and some molecular synthesis agent. Google released the version of an AI co-scientist, I believe it was 3 months ago or so, that also have different types of agents. So think about it as a compound AI system. There are multiple types of agents to do generation, or to do reflection, or do ranking. And it's an agentic workflow together that is focusing on helping the scientists to do discovery and so on. As I mentioned, Claude has a research feature right now that goes and searches the web for you and brings papers for you. And ChatGPT also has a deep search capability. But why isn't it fully integrated in our scientific workflows? What's still missing? How can we make sure that it's brought closer to the actual research needs and research infrastructure? So first of all, it's fundamentally not cross-disciplinary, and it's a big problem, right? So future houses models that are focusing on the bioresearch, and other models, for example, Google, I think it's more AI ML, and it's just like looking into the siloed domains. Multi-turn interactions are not really enabled, and there is no way to kind of reason across disciplines, across multiple steps, which is really challenging. And I bet all of these companies are working on it, but it hasn't been solved yet. They are primarily using agentic AI workflows. Agents are there, but not the whole compound AI system. It's not integrated into with the current domain-specific tools or into the research infrastructure. It's barely multimodal, so right now we're still testing images and tables, and there are research prototypes there, but we are not integrating ontologies, domain-specific ontologies, scientific databases, knowledge graphs. This is not there yet. And finally, the industry systems are less user-centric. It's not looking into the workflows. It's not driven by the needs by the end user, the scientist that needs to write code or needs to run the experiments or plan the experiments or do the evaluation or hypothesis validation. So that's the current need. The systems are there, but there are a bunch of things that we need to be working on. And I wanted to show you this recent press release by Future House that claimed that their agents, and I showed you multiple types of agents that they have, they made scientific discoveries. So these agents, they went and they searched, they had a hypothesis, they did the investigation all by itself, and they discovered a specific treatment. I believe for like the cataract, some specific type of cataract. And that was the first real discovery that this agentic AI systems did. And it's literally from 7 days ago. There is a lot of potential there. So what are we doing and how are we trying to solve it with compound AI? And how are we addressing the needs of current research workflows and the needs for scientific discovery across disciplines? There are multiple efforts that we have been working on. One is the DOE Bridge Science effort that is focusing on material science and nuclear security and AI, and the second one is BioSage that is focusing on AI, biology, and biosecurity. And our goal is to develop a system using the user-centric design to make sure that we integrate different frontier models, retrieval augmented generation, agents, and domain-specific tools, as well as structured data and knowledge graphs to make sure that we address the challenges for the scientific workflows. Okay, let me guide you through the interaction steps with models, agents, and tools. So imagine there is a scientist is asking a question it's a question on the intersection of computational sciences and biology, or a biomedical domain, where there's a question about the GNNs, graph neural networks, and their specific application to a specific domain task. As you can see, after the query is issued, the agents go and work, and specific types of agents identify what type of workflow, whether it's a summarization or discovery, or it's a translation, or it's a brainstorming workflow. There is another one we're working on, which is experiment planning, which is a separate research workflow. So the agents return answers, and the agents return answers in a summary format, which is like kind of summarizing across papers into a specific chat and provides evidence. That's what I found in this paper or in this report. And then the scientist is interacting with the output and making sure that the final result is summarized in a structured format, and it can be a table, right? And as I mentioned, there are multiple types of workflows. We're focusing on these first three: summarization, debate, and brainstorming, and we're testing them with the end users. How do we implement agents, and how do we do the evaluation will be then the next steps I wanted to cover. So if you look into our agent profile. Agents have behaviors, they have summaries or backgrounds, they have goals, and they have different memory representations. So as I said, agents are this autonomous, LLM-driven, we also call them cognitively inspired agents that interact with other agents, and they also interact with humans in order to enable this agentic workflows. And there are really cool papers that I got inspired by about cognitive architectures into language agents or LLMs, and that led to the development of that agent implementation that we are reusing not only for this compound AI systems, but for other systems. And I can tell you about human digital twins, or focusing on the social cyber domain, where we have different agents that are creating content for different information operations and so on. So the architecture is very similar. That includes decisions, behaviors, profile, and the memory representations. So how do we put it all together? That's a quick summary of the backend. So we're using Llama Index and a vector database from OpenSearch. We're using currently Pedantic AI for agent orchestration and specific embeddings that we experimented with. Again, it's not a prescription, but that's what worked really well for this application. As you can see here, we have multiple disciplines: biochemistry, AI/ML, molecular biology, and we have retrieval augmented generation tools, and you have agents, which is query planning agent or reasoning agent or translator agent, response synthesis agent, things like that. The user is interacting with the interface, current prototype, and we log all of the interactions, and then we take the results of interactions, and we can analyze them to see where they break and where the breakage points are in order to improve. So we're basically learning from that interaction data to make sure that we improve future interactions with the system. This is currently the data that is behind the implementation. It's fundamentally cross-disciplinary, but that's a prototype system, and any other data can be added here. There are plenty of there's plenty of research artifacts that are behind the paywall, but there are also plenty that are open source and not OpenAI. AI2 in Seattle, they released a large semantic scholar data set that can be leveraged for scientific research and for testing and experimentation. So how does the retrieval happen? So for the retrieval agent, as you can see, there are multiple domain-specific agents that queries the data in a certain domain and return the answer back. And then the synthesis is happening across multiple domains. So it looks simplified here, but there is a lot of prompting that goes behind the scene here. Make sure that the agents that are driving the retrieval and synthesis, they are returning the end user what is needed. And then reasoning is way more complicated. So reasoning right now, we're focusing on three types of reasoning: macro reasoning, micro reasoning, and metacognition optimization. So it's a schematic diagram of what's happening and how we're prompting different agents to reason across disciplines. And also what's important to say, let me jump to the next slide. We are currently working with multiple modalities, but we still project everything into the text space, right? So we are not working with the like image models or anything, right? So we take an image representation, we summarize the image in text, or we summarize the table in text, and then in the text space, we basically operate and put all of these inputs or insights together in order to gather the final evidence, and that's how we work across disciplines. So obviously, more things have to be done in terms of multimodal, but that's what is currently implemented in the prototype. Okay, so hope I wasn't going that fast with the development. So I briefly covered the kind of the way that we are implementing it and what is happening in industry. Evaluation is another big challenge. I'm showing you a few papers. One is focusing on analyzing the gaps of current evaluation for scientific research assistants specifically. And another one, the Open Scholar one from AI2 is presenting actually the benchmark and the data and the way to do the evaluation for scientific retrieval and scientific literature specifically, which is a very narrow domain. So what I'm trying to show with this slide is make a point that in general, AI evaluation and generative AI evaluation, regardless of the domain, whether it's the science domain or something else, is fundamentally broken. The way that we do it with the current benchmarks and leaderboards do not give us any evidence, do not provide sufficient evidence that the system is not gonna fail or is not vulnerable on the real data and the real use. So what we have been doing here, we have been analyzing what are the existing benchmarks specifically for the science workflows. How do we do compared to other systems? So we kind of baselining. And what else do we need to do? And that's what I wanted to focus the second part of my talk on. What else is missing and how can we improve the evaluation for the science workflows and beyond? So here we're listing multiple benchmarks focusing on scientific workflows. Some of them are very well known. Some of them already included in the systems like GPQA. That benchmark is from 2022. It had been read by all of the models that are out there, GPT-4o, anything that was trained after 2022 include GPTQA. So there is no point really using GPTQA to do proper evaluation because it's already in the LLM memory, right? It's already there with the answers. There are some benchmarks like LitQA and LitQA version 2 that was developed by Future House, that startup that I mentioned. It's very small, it's 100 questions, and it's primarily focusing on scientific literature retrieval. There is another one which is larger, 3,000 questions, WMDP, which is focusing on bioscience and cyber knowledge testing. And the Humanity Last Exam, it's the most recent benchmark that includes very, very complex questions. I encourage you, if you are not familiar with it, just go and check. Very complex questions from all over the world. It's really complicated. It basically shows that all of the models that perform at 80% accuracy on MMLU or GPQA, they do like up to 10% on this more difficult benchmark. But again, it's great, more difficult benchmark. It's not cross-disciplinary, and it's barely multimodal. I think it's just images and text. So more has to be done still in the benchmarking space, but that's a pretty kind of sophisticated overview of what are the benchmarks that exist for scientific workflows. To give you an idea how these benchmarks look like, you're all scientists, right? So if you look into, it's primarily multi-choice questions. So the way that we evaluate compound systems or frontier models, we're asking a question and we give four answers. So it's not an open-ended answer, but it's just like a multi-choice QA pairs. LitQA, as I said, focusing on the biospace, WMDP, it's bio and cyberspace. And then I'm going to show you a few others that are in a similar format. But what we've done, we did, similar to other systems, we did test our implementation using the open source models Llama 3 and GPT-4o as a baseline. And then we did the ablation. We just take vanilla model, then we take vanilla model with RAG, or retrieval augmented generation, and then we take the agentic workflow with reasoning and retrieval. So right now we testing the retrieval agent, and as you can see that the adding, right? So we are not eliminating anything. So compounding, adding the agents significantly improves across GPT-4o Llama on LitQA evaluation, and then similarly on WMDP. We see that both retrieval augmented generation and retrieval agents and agentic workflows give us better performance. If we move into Humanity Last Exam benchmark, you can see on the right-hand side, it's a very complicated question for chemistry in this case. And then we also testing a less complicated benchmark, GPQA. We see that the performance is mixed, and it's explained because the GPT-4o already has, like if you look into the GPQA result, if I just use GPT-4o model, which is trained on the whole internet, including GPQA, the model by itself gives us better performance, and we don't even need to add any additional knowledge, right? So it's totally overfitting the benchmark. And then in this case, we see that for the humanity last exam, which is interesting in that RAG, exposing the model to the external knowledge is giving us better performance, even better than the agents. Okay, so what does all of it mean? Yeah, so we can compare to the vanilla models, we can compare agents to the retrieval augmented generation, and we can also compare ourselves to other systems, right? So we can baseline. But this is still for a single domain. We fundamentally developed the system that goes and reason and retrieve across domains and synthesize knowledge altogether. So we need to develop our own benchmark, and that's what we did. So we developed a benchmark using the reasoning GPT-01 model that wrote these types of questions. We prompted it in a specific way, and we experimented with the way that we prompt the reasoning model. And then we created a benchmark that is focusing on AI and biology in this case. So it's 100 cross-disciplinary QA pairs on the intersection of these two disciplines. So we, as I mentioned, we're using zero-shot prompting approach in order to generate these questions. And then we use this benchmark, which looks like that, right? So this is still multi-choice questions with reasoning, right? So it's a little bit more complicated benchmark that we compare against. We use the benchmark to test the improvement that the compound AI solutions give us. So on this plot, I'm showing you the performance gains over the vanilla model, right? So when we add RAG, we see a lot of performance improvement. And when we add different versions of our retrieval agents, we don't see performance improvement for like the baseline agent for the GPT-4o. And then we tested Llama 5.4 models, so basically open source and closed source models. So as you can see, if you're using a closed model, the performance improvements are much higher, but then 5.4, which is a much smaller model, not even comparable, but you see, you don't see the performance boost there. So obviously the investigation is still in progress, and we currently creating a multimodal benchmark that is spanning across multiple disciplines, and these results are coming. But that's the first, to my knowledge, cross-disciplinary benchmark that exists that allows us to ask questions that span across two disciplines, that require more than just going and searching and finding the answer in the data in the paper and returning it back. And that's what all of the other benchmarks are doing. So let's talk about evaluation broadly. More broadly, I bet you're all familiar with the NEST risk management framework that clearly describes that the dimensions for AI evaluation beyond accuracy, beyond performance. Obviously, systems have to be performing, but they have to be safe, they have to be reliable, they have to provide transparent outputs. How do we actually implement it in practice, and how do we test it? We're still not there yet. We don't have a good way to do it. And then we don't have a good way to do it for the frontier models. Right now, we're working with the systems that include models, agents, RAG tools, and so on. And that's one aspect. The second aspect is red teaming, right? So how do we know that the system or the agents within the system haven't been misused? And there's cool research from MIT. They have been trying to outline these risks of specifically generative AI, and I think kind of agentic AI. That is really recent, and the risks are outlined, but I don't think we have a solution yet on how to address the risks and how to think about them and how to implement it. The AI Safety Institute in the UK released a system, I think it's called Inspect AI. That was probably last year one of the tools that allowed to do proper experimentation and evaluation of frontier models. But it doesn't address the challenges of agentic AI evaluation. And literally people, like I'm citing 3 papers here, which are from, I believe, a couple of months, that outline the failure modes for agentic AI systems, and think deeper about security risks and safety risks of AI agents, foundational agents. The way that we think about it, we're using causal discovery. We really need a way to investigate the behavior of the system if you manipulate the different components. So when you use a specific data, or when you use an agent, or when you use a retrieval augmented generation. So you can do these different ablations, and I want to be able to test the system and reason about system failures when I am manipulating, right? I'm manipulating the inputs. I see the effect of the manipulation on the output. So that's the way that we're looking into a compound AI evaluation. We have causal analysis tools. We're leveraging some that are pretty widely used, like DoWire or EconML. We're using two approaches. One is causal structure learning. So imagine you have different treatments in your evaluation framework, and then you having outputs, and your outputs is the way that the system performs, and other types of other properties of generated content. We want to make sure that the compound AI system, when it interacts with the user, it not only reasons in this interaction and provides evidence, but also it shouldn't be that long, right? When the system goes and searches for 2 minutes, this is not gonna work and help and improve my workflow. So the answer should be concise, it should be readable, it should be interpretable, it should be spot on, right? It should be performing. So all of these characteristics of the system can be analyzed, and then depending on the design choice that we make, whether it's a model kind of llama or GPT-4o as a baseline, or whether it's a specific data set or a specific question or a specific domain, we want to see the effect of that intervention on the system behavior using two methods. One is causal structure learning, and the second one is treatment effect estimation. So causal structure learning models, they allow us to to see a big causal graph of what affects what, like the provenance graph, which is more difficult, more difficult to get, and more difficult to comprehend and act on. The treatment effect estimation allows you to manipulate one treatment variable and to see the effect on another one, right? So it's so think about like an edge in the graph rather than the whole graph by itself, which is a more complex task. So this is the initial evaluation we performed for the BioSage system. So as you can see here, the columns include different measures that focus on quality of the generation, the structure of the generated output, the readability, and the quantity of generation. We don't want it to be too long, too short, and the red cells show negative effect, and the blue cells show positive effect. So as you can see, for example, LitQA is a very challenging benchmark, and there is a negative effect on performance. So the questions that are there, they are more complex. You see that the readability indices like Fletch and Fletch-Kincaid and SMOG index across most of the data sets and benchmarks and ablation experiments, the output is pretty readable except of a few exclusions for like GPQA and LitQA. So in general, this is a very good way to kind of open the door, open the books, and understand what are the manipulations that I'm making to my implementation of the system, and how these manipulations affect dimensions beyond performance. But it's still not enough. So that's the first step, and I think causal discovery it would be a pretty powerful tool to do it and kind of go beyond just accuracy measures and benchmarking. But recent work, I wanted to show you these 3 papers from Nature that are looking specifically for the biomedical domain. They basically found that AI with the doctor is worse than AI by itself, which means that the doctors, the end users, they do not know how to properly leverage that very powerful agents, LLMs, augmentation, right? So what do we do to fix it, right? So how do we include the human into that evaluation process, and how do we ensure that AI is augmenting, not degrading the performance of the human AI team or human AI system. And that's what we have been doing through modeling and simulation and evaluation on another DARPA effort. The effort is called MHAT, Empirical Models of Human AI Teams. That is focusing, it's focusing more on the DoD application. So we tested it on a search and rescue mission in a simulated Minecraft environment. But the idea can be propagated to the science domain or the medical domain, like AI was the doctors or AI was the scientists. So imagine you have different, we call them human digital twin agents that have similar background that I showed you was the agentic implementation. And we're simulating how these digital twins that represent the humans with personality and behaviors are interacting with AI teammates. And we explicitly turn the knobs. We explicitly say, we can adjust the competency of the AI, we can adjust the competency of the end user, we can adjust the propensity to trust, personality traits, reliability, or maliciousness of the AI, and so on. And then we measure how these different teams or how these different simulated human AI teams with manipulations are performing, right? So we have a really sophisticated human AI measurement set that focus on team processes, which is coming, all of this is coming from like team research and team science research. We focus on team processes, team emergent states, and team outcomes. The way that it could look for similarly for the research workflows, imagine you have real world interactions between humans and the infrastructure, scientific infrastructure. All of this is recorded, all the logs, right? But sometimes you don't have enough of it, right? You can only have like a small scale of me interacting with a specific instrument or a user interacting within a specific database, you name it. But then what you can do, you can actually simulate it at scale. So think about large scale simulated interactions with interventions, right? So you can say that what to do if my database fails, what to do if the user is less competent, right? And you can simulate it. And then what you can do, you can use causal tools and predictive tools to anticipate when there will be these friction points between the end users and the AI systems or components of the compound AI system. And you can explain, right? Like you can explain the interventions and you can say that, oh, if I do X, if I manipulate X, this is going to lead to less trust within my human AI team. And that's what we did, as I mentioned, for the DoD scenarios. But I think there is a lot of application and potential to do this, to kind of move beyond AI model evaluation and beyond compound AI system evaluation, benchmarking, even causal analysis, but then step way back and try to analyze how the end user is interacting with the scientific research workflows and what are the effects of these interactions. Can we anticipate the friction points and can we make it better? Can we optimize it? So this is the another demonstration I wanted to show, which is focusing on different properties of the users or human digital twins and properties of the AI. So as you saw, there's like propensity to trust, and there are different reliability for AI, and different measures like help assistant, team coordination, different analysis of team communication, which is like empathy, sentiment, other things that we can derive from the way that humans are interacting with AI systems. And it's an interactive dashboard that allows you to analyze successful or failed human AI interactions. It allows you to do the comparison and analyze the effect of intervention. That has multiple plots. And in this case, we have the ground truth data, so we can ground our simulations. So we have real humans working with AI in the Minecraft environment. And then we have simulated humans working with AI in the same environment, and we can compare the ground truths versus the simulated outcomes. So I will stop here for the sake of time, and just this is my last slide. So I wanted to send the final message across 5 dimensions, and just bring up this important point is that we made a lot of progress with AI agents and and different compound AI components, but we still fundamentally don't understand and can't model and prevent risks that are emerging between humans are interacting with these agents, when the agents are interacting autonomously in the environment like the web. You can see there are plenty of agents that are booking things for us and doing things autonomously without our intervention. And also how humans are interacting with the environment, this web environment, social media, and so on. So the 5 key final messages I wanted to say that we really need to focus on seamless integration. That's why this research has to be done with the domain experts in the loop that define the requirements for the scientific workflows. Autonomous scientific workflows focusing on like going from hypothesis generation to validation and experimentation is the key. Doing it across disciplines is another big challenge, and I think we can get there if we only look across disciplines. We need to build trust in human AI partnerships and do proper modeling and simulation and look into the AI that we are developing and agentic workflows with the human in the loop. And finally, we need to make sure that we're democratizing our innovation, and we're doing it with the open models, not only closed models, which as we see, they are more performing. But all of this, I think we are on the right track, but we are not there yet. And a lot has to be done, especially looking to the safety and security of compound AI solutions for scientific discovery. And that's my last slide. I have papers by our team, and I want to thank the team that is behind all of it. And I'm ready for the questions.
Thank you so much, Svitlana. Great presentation. Very interesting.